Hi, welcome to this lecture on environmental adaptation of animals. Now we will end the muscle section to look a little bit on the variability on the circulation. So, if we think on the mammalian heart, we have the left and right atrium and then left and right ventricle. But we quite often think that it's the one compound, so we have one heart. And from the left hand side we get on the systemic aorta and get the blood that is oxygenated in the lungs on all organs. And then when it comes back on the right hand side, then it will be pushed on the pulmonary artery. And therefore we actually can put it in a little bit different way. So the right hand side, the right atrium, right ventricle, they are actually a right heart. So there's a pump that is not doing anything but pumping the blood in the pulmonary circuit, so in the lungs. And from the lungs, of course, what we get there, we get oxygen. And we can remove carbon dioxide. And this oxygenated blood is coming back and it's pumped with this second heart, this left heart, with the high pressure to all organs, so in this systemic circuit. So actually, although it's working together, so the right ventricle and left ventricle, they are regulated at the same time. It's still in this systemic way is that we are working with two hearts that are just in the same place. The fish have four-chamber heart. There is a sinus venosus with smooth muscle, very thin layer. Then there is atrium that is also a quite thin, ventricle, and bulbus arteriosus. They are all in a line, so there is no two hearts. And this bulbus arteriosus, it's a completely, quite often it's quite completely white tissue. It's elastic tissue and it smoothens the pressure, so it's even difficult to break because it's bent so well. And there's no heart between the breathing organ and the systemic circulation. So the basic idea that we have the gills, and from there we have, for example, the brains. And in the gills we have capillaries, as well as in the brains we have the capillaries. And that means that in this blood pressure is dropping at least by 20%, even 30% in the gills where we have the capillaries. And therefore, in this dorsal aorta where we have the oxygenated blood, the blood pressure is anyway way much lower than ever in mammals. We can of course compensate it a little bit by having a larger heart or more effective heart, so it would push more blood per each beat. But anyway, these gills are lowering the blood pressure very drastically. And when it comes back, this blood over here is coming back to the heart, and in the heart it's now giving the oxygen. But for example, guts and liver and kidneys, etc., they've been using already as much oxygen they need. So there's not much any oxygen available in the worst case. And for that reason, we might have in some animals in some fish we have the compact myocardium. So the idea is that in general the fish heart is having the least oxygen of all tissues. And in athletic tissues, they have the compact myocardium, where you have these tile-looking cardiac myocyte cells binded to each other to increase the cardiac output. But the problem is that, okay, when they are binded together, how on earth they can get any oxygen? You need there also some capillaries. And therefore it requires coronary arteries to allow the fully oxygenated blood. So in these capillaries, you must get oxygen-rich blood. And in the compact myocardium, the fish are very they can modify this tissue very drastically. So in different populations, for example in this athletic trout, they might have in some cases 35% of the heart is compact myocardium. In some other populations it's 45%. And in those populations where they have more compact myocardium, they are traveling on the river long distance. Or there's a large flow of water. So the river current might be there's a huge steam against which they must fight to get on the breeding areas. So for example, this population over here, it travels maybe a little bit over 100 miles, and then but at the same time it must travel and use much power to swim against this river current, because in this river there was a huge current in the springtime, and therefore it needs more compact myocardium. And how it can be done is that from the chill, when you have the heart, then the chills. From the chills you can get coronary arteries. Okay, so that's one possibility. What about then on terrestrial vertebrates? So in the general plan in the fish is that, okay, you have in the gills you have the oxygen, and then in these athletic fish you can have also coronary arteries. But what about then on other vertebrates? First of all, in the amphibians we might know that, okay, we have 2 atrium and 1 ventricle. And so if you have one chamber, it will mix the blood that is coming from the systemic tissues as well as that blood that is coming from the lungs. But although it's one chamber, it's only partial mixture. So mainly the systemic tissue blood is flowing on one aorta to the lungs, as well as on a little bit on the skin, and then this oxygenated blood is mainly flowing to the systemic tissues. So it's not completely handicapped on this. Then, of course, we have in the mammals, we have two completely separate heart systems. And this is giving the opportunity that, okay, there can not be any mixture. And therefore, the systemic tissues will get as high oxygen concentration as possible. Then the turtles and the lizards and some snakes, they have a little bit a modified version of this amphibian model. So there's two atrium and one ventricle, but this ventricle actually can be even mechanical separated. So when it's contracting, it's divided in two parts. And in that case, you can get even more this oxygenated blood on the systemic tissues and less on the lungs. Also, what you can see that in the snakes and turtles and lizards is that the skin is getting the blood from the systemic tissues. In the amphibians, it might be using also to get the oxygen from the surrounding, but actually it's more used for getting rid of the extra carbon dioxide that we are going to discuss next week. Then, of course, the birds, we have pretty much similar and as in mammals, so it's completely two separate heart system. But one exception is that, okay, the crocodiles. So the crocodilians, 4-chamber heart, but there are a lot of these tubes over here. So it actually have two aorta, and these aortas are mixing the oxygenated and the non-oxygenated blood. And why it can do it? Okay, this is the heart of the crocodilian, and from the in front of the right and left ventricle, over here we have this weird looking system. So these aortas are interacting. There is a gap between two aorta. And this means that when we are steady air breathing, we can get oxygenated blood on both these aorta. But then, when they are diving, we can get oxygenated blood and less oxygenated blood in different tubes. So therefore, you can hold your breath a little bit longer. Thank you.